Hi guys, welcome to my YouTube channel Aerospace Design. In the previous video, we have seen how to install ANSYS Students version at free of cost. In today's video, we're going to see how to do a stress analysis for your flat plate with a center hole. For that, first we have to do is go to Start and then type ANSYS Mechanical APDL. ANSYS Mechanical APDL and go to ANSYS Mechanical Product Launcher. So for example, I'll directly go to the particular file by clicking the Start option and then click on Mechanical APDL Product Launcher. So after clicking on this particular file, you can able to visualize this particular dialog box. Here you have to give it as simulation environment as ANSYS itself, and then in the license you give it as ANSYS Academic Teaching Introductory, and in the file management you give it the location as working directory, C users LCOR as per my wish. So according to your system, your configuration, wherever you want to save the file, make a folder over there and give the name and accordingly save the file by using this browse option. And then similarly you give the job name for that particular working directory. Then click on run. So after clicking on run, you can able to see that the software is being initiating to open up the dialog box for you. So once this is done, after clicking on run, you will be getting this particular dialog box, as well as you will be getting this output dialog box. So in this output dialog box, you can able to see whatever the input files you are giving. So that is like your boundary conditions or meshing or whatever the input parameters you are giving. So that you can able to see here. With respect to that input parameters, whatever the output you are giving, that is like after solving the problem, whatever the output you are getting, that also you can able to see in this particular window. So that's what the output window is all about. So this is a background process, you don't need to worry about this. So don't close this dialog box, always keep it minimized. And then this is the actual window where you're going to do the analysis. So before starting the analysis, I will tell you these are the utility menus which is helpful to analyze the problem. Similarly, these are the options or the menus which is available as it is called as main menu. And then these are the options, we call it as the user control menus. So now the problem, so what is the given problem we are going to see here is a flat plate with a center hole and it is having a uniform thickness. When you are applying a load at one end, what happens to the plate? So we are considering it as the plate as a fixed end on the other side. So it is like a cantilever beam. So one end is fixed, the other end is free. So you're applying the load at one end and the other end is fixed. So due to that, how the deflection has been taking place. Due to the deflection, how does the stress has been taking place? So that's what you're going to see here. How does the stress is taking place as well as how does the strain has been taking place. With respect to your stress concentration factor and in the governing equations used here as the one versus stress equations. So now, approaching the problem, first we have to know what are the options available in main menu. So we are going to mainly use the four options. The first one is preference, preprocessor, solution, general post-processor. So preference is nothing but either we are going to do a structural static analysis or fluid flow analysis or thermal analysis. So here I'm going to do the structural analysis. So I will go to preference and click on structural and click OK. So once preference is done, go to preprocessor, element type, add element. So just go to add and then click solid 8 node 183. So why we are using solid is all about because we are going to analyze a flat plate. So flat plate is nothing but having a solid element. So that's why we are going to just put a solid. And then 8 node 183 is like 8 nodes and then 183 is the element area of the particular nodal points. So then click OK. Then go to options and click the element behavior K3 as plain stress with thickness because we are going to assume the thickness is constant. So just give it as plain stress with thickness and click OK and then close dialog box. Then go to real constants and click on add edit or delete and then click add plain 183. Just give the element type as plain 183. Click OK. Then give the thickness as value of 0.5, which is assumed again. So this is your uniform thickness throughout the plate and click OK. Then close this dialog box. Then go to material properties. So again, material properties, depending upon the Poisson's ratio and then the Young's modulus, any material we can able to choose. So either it can be aluminum alloy or titanium alloy or carbon fiber reinforced polymers or Kevlar carbon So whatever the material you want to choose, you can able to give the material properties of that particular material, and we can able to analyze over here. So go to material properties and click on material models. After clicking on material models, go to structural, linear, elastic, and then isotropic. So where the material properties are same in all the directions, so we go with respect to isotropic and give, and here I'm considering the material properties aluminum alloy. So I just give it as the Young's modulus is 70 gigapascal, 70 e power 09. So I just give it as 70 gigapascal. So giga stands for 0 power 9, e power 09. So Poisson's ratio is 0.33 and click OK. Then close this dialog box. Don't forget to close the dialog box. If you're not closing this dialog box, again you will be facing some problems. So make sure that you close this dialog box. After closing the dialog box, go to modeling. So where you have to make a rectangular plate. So go to modeling, create, okay, areas by rectangle, and then clicking by two corner points. Give the x coordinate as 0 and then the y coordinate also 0. Then width as 100. So the rectangular plate width is 100. We are assuming it as, and then the height is 50. So this will make a rectangular plate over here. So we got the width as 100 and then the height as 50, and this particular origin point as 0, 0. So now we want to make a center hole. To make a center hole, we need to know the center point. So it's just basic mathematics, that is like your coordinate system. So we have to get the center point over here, and we have to get the center point over here, that is like a centroid. So width divided by 2 and height divided by 2, we will be getting the centroid. And with respect to the centroid, if you draw a circle with a diameter of 10 or radius of 10 centimeter, then we can able to get the circle of it. So just go to circle, solid circle, and then click your x value as 100 divided by 2, that is 50, and your y value 50 divided by 2, 25, and then the radius of the circle we just take it as 10. Then click OK. So now we can able to see the circle has been created. So we have two areas over here. The first area is a rectangle area, and the second one is nothing but your circle. After the circle has been created, just go to operate under the modeling options and click on booleans, subtract, areas. So we have to subtract the two areas. The first area is nothing but the rectangle minus the smaller one. So first we have to click this rectangle, it will turn it as pink color, then click apply, then select the inner circle, so the second area, and then click OK. Now you can able to see that the subtraction is done, the boolean operation has been done properly. So you can able to see that the first area minus the second area, we get a hollow hole over here. So this is what we require for the modeling of a simple rectangular plate with a center hole. Then go to meshing and then go to mesh tool. So what is meshing? So meshing is all about you're meshing the entire plate with respect to your nodal points. So since it is a FEA package, finite element analysis, we know the nodal points helps to capture the stress concentration factors. So more the number of nodal points will be getting more accurate results. Lesser the number of nodal points will be getting less accurate results. So to get more number of accurate results, like we have to go with respect to higher number of nodal points. To go with respect to higher number of nodal points, again you have to purchase the licensed version, and then the system configuration should be high for that. Okay, so now we are using your the student version, so we have only limited with respect to 32,000 number of nodes, so we cannot able to go beyond that. So we are restricting within 32,000 number of nodes. Okay, so now we have this rectangular plate, we are going to mesh this entire rectangular plate. So to mesh this entire rectangular plate, first I go to lines, set, and set all the outer lines and click apply. Then give the number of element divisions, how much the number of element divisions I want. So I just let it be 50, as simple as possible. Then I just give 50. Okay, so this entire line has been split down into 50 smaller elements. So similarly, the vertical and the horizontal, all the 4 lines have been split down into individual elements. So individual 50 elements. Now we have to make the same thing for this inner circle also, because wherever there is unsymmetrical shapes, for example, there is arbitrary shapes over there. So over there we have to capture with respect to more number of nodal points. So in that case we have to give more number of nodal points over here. So again click on mesh tools and click on lines, select this circle, click OK, and give here instead of 50 I just go maximum number of points, like let's say 75, so that I'm not crossing more than 32,000 number of nodes. So I'm just giving just 75 and click OK. So now we can able to see the entire circle has been split down into 75 smaller number of elements. So once you mesh it, so this particular 50 number of elements, and then this 75 number of elements will be contributing and finding solving the mesh with respect to the nodal points. Then again click on mesh tool and then click on triangular mesh. So that will be easier whenever we're having a curve shape. If it is just a rectangular shape, then we can go with respect to the quad mesh. So here we're going with respect to the triangular mesh, and then click on free and then click on mesh, select the area to be meshed and click OK. Now we can able to see that the entire area has been meshed. So this meshing process has been taking place. Now we can able to see that the nearer to the hole there are maximum number of nodal points, and away from the nodes away from the hole will be having lesser number of nodal points. Okay, so next go to plot, and by clicking on nodes we can able to visualize the smaller number of nodal points. You can able to see there are a number of nodal points over here, so which is not crossing 32,000 number of nodes. Okay, so always keep in mind that you are using your free version, so it is limited with respect to 32,000 number of nodal points. So always give less number of nodal points. If you have a licensed version, then you can go with respect to lakhs and lakhs number of nodal points, which will capture the much more accurate results. Okay, so this is the meshing process is done. Next we are going to the boundary condition. To go to the boundary condition, go to loads and click on define loads, apply structural displacement on lines. So select this entire line which you want to do the meshing process and click OK. Then click on all degrees of freedom and give the displacement value as 0 and then click OK. Now we can able to see that towards the left hand side of the plate it is a fixed end, so it's been shown with respect to the both the sides degrees of freedom has been fixed. But towards your right hand side we have to give the load in the upward direction or the load in the downward direction. So depending upon our conditions, so the load has been applied either in the upward or downward direction. So here we are considering with respect to the upward direction, so we have to give the load in the upward direction. So here in ANSYS APDL we cannot just give the load directly in the upward direction. First we have to use this coupled degrees of freedom, so we call it as coupling equation. So go to coupling equation under preprocessor. So click on coupling and then click on coupled degrees of freedom. And after clicking on coupled degrees of freedom, go with respect to this option called box and then zoom in and select this entire box. So this is like a pan option. So pan towards your right. I'm just panning towards your right. So yeah, so we have to pan towards your left. So click a couple of times and until you get a proper view of it. Then select only the corner lines or the corner nodal points. Okay, so just select only the corner nodal points by clicking here point outside the box and drag it and select only this particular points. So now you can able to see all the nodal points on the corner line or the free end has been selected and click OK. After clicking OK, give the set reference number as 1 and give the degrees of freedom or the location along your UY direction, so that is in the upward direction, and click OK. So now we can able to see that whatever the load you're applying, so all the nodal points over here has been combined as a single line. So you can able to apply the load in the upward direction. So you can just give fit to view. So this is fit view. Then everything will come and fix within the given screen. Then go to loads, define loads, apply structural displacement. Sorry, displacement we already given. Now we have to give the load in the upward direction. So go to force on nodes. Okay, so I'm giving the force on the nodes in the upward direction. So I click any 1 or 2 points on this particular line and click OK. So I'm going to give the load in the upward direction. So upward direction is nothing but y direction. So I'm going with respect to force along y direction. Fy represents force along y direction and Fx represents force along x direction. So now I'm going to apply the force along y direction. So I give it as Fy and then the constant value. So I consider some value. So let's say whatever the lift force or whatever the load acting on the particular plate we consider. So I'm just taking a constant value or some assumed value as 100 as the load in the upward direction and click OK. Now we can able to see that the arrow mark is in the upward direction. You can able to see that the red color arrow mark is in the upward direction. So we can able to come to conclusion that the load is being applied in this upward direction. Once the load is applied in the upward direction, go to solution and then go to solve current load step. So why I'm doing this is till now whatever I've given is like the loads or the boundary conditions, and then meshing I have done, and then I have made the modeling. So everything is done properly. Now I'm going to solve this problem. So whatever the given conditions are given, one end is fixed, the other end is free, and applied the load on the free end. So your deflection will be in the upward direction, and due to the deflection in the upward direction, the material properties, your Young's modulus and Poisson's coefficient will be varying, and then you will be getting your change in stress concentration factor or stress concentration factor, where the maximum and minimum stress takes place at that particular nodal point. So that's what the stress concentration factor is all about. So we can able to find out the maximum stress concentration factor as well as the minimum stress concentration factor with respect to the governing equation. Then go to solve current LS. So click on this option, then the dialog box will come. So click solve current load step. Yes, click OK. Now it's been solving the entire problem with respect to the governing equation. So what is governing equation? At each and every nodal point, the governing equation will be taking place. So that is like all the governing equations of your stress, strain, and then other equations which we have learned through the equations or theory part. So those equations will be running behind the software and will give you the proper output. Then close this dialog box. So if you're getting solution is done, then whatever the boundary conditions, what are the preference you are given, everything is correct. If you're not giving it properly, then the problem won't have been solved. Okay, so the convergence has been done, so iteration is done. So next go to general post processor and click on read results last set. So I am doing this is because if you are doing more than 2-3 options, then we can able to visualize the last result, so last solved result. So that's what I'm going with respect to general post processor read results last set. After clicking this particular option, go to plot results counter plot. So I'm going to counter plot because we have solved the entire problem or the flat plate with the center hole with respect to the nodal point. So the nodal points are the points which helps to visualize the stress concentration factor or the stress concentration point at that particular nodal point. So to visualize that, we are going with respect to counter plot and then nodal solution. After going to nodal solution, we'll be getting this particular nodal solution data. So the outputs, we can able to visualize all the outputs over here. So first I'm going with respect to the stress, and then click on von Mises stress. So why von Mises stress? Because von Mises stress is a stress which helps to identify the maximum stress and the minimum stress at a single point. So we can able to have 3 equations at this particular point, and then we can able to visualize the maximum stress of that particular point and then the minimum stress of that particular point. So if you want to go through much in depth, you can able to Google the video of von Mises stress, how does the stress has been taking place with respect to that. Okay, so that is what the von Mises stress is all about. Then click OK. Now we can able to see how does the output has been created. So we can able to see that the maximum stress is represented as the red color and the minimum is been represented with respect to your blue color. So intermediate is been representing the lower to higher order terms of your stress range. Okay, so this is how we have to visualize the result. Okay, so now to visualize exactly where the maximum stress is all about, then we can able to animate this particular output. So to animate it, go to utility menu and click on plot controls, and then come to animate and then click deformed results. Over there we have stress, and you just check it with respect to your y direction stress and click OK. Now we can able to see that the maximum stress has been taking place nearer to the hole. So this is the theory also states whenever we are having a flat plate without a hole, the maximum stress will be taking place at the fixed end. But at the same time, for a cantilever beam, whenever we are having a hole with respect to the fixed end, okay, so there is a fixed end and there is a hole also, then we can able to say that due to the applied load, the maximum stress will be taking place nearer to the hole, not rather with respect to the fixed ends. This is because the wave which has been propagating from here is being opposed by this particular hole, and then maximum stress concentration has been converging over here. So that's what the maximum stress has been created over nearer to the hole and then minimum to the fixed end. So since the load has been applied in the upward direction, we are getting maximum over here and over here. So over here it's been minimum. That's what the understanding we can able to consider from this particular diagram. Then close this dialog box. To save this output, if you save as it is, then you will be getting the background as black color. So if you're going with respect to your cartridge or a black and white printout, then this cartridge will be wasted. So to avoid that, we are going with respect to change this background color as white, so we can able to save the cartridge and we can able to get the proper output. To save in such fashion, go to plot controls, write meta file and click invert white or black. After clicking invert white or black, then click on the folder where you want to save the file. So I'll just give it as desktop and give static structure analysis. 1 2 3, then I'll say the file save as okay. Now to visualize that particular file, if you want to see, I will show you here. The static structural analysis 1 2 3, the output, the background will be changed into white color. Can you see this? So this is the background which are having the same thing, but it's been changed to white color, but then the image has been kept as it is, so that we can able to save the cartridge as well. Okay, so this is how we have to do the stress analysis for your flat plate, and there are a lot of concepts behind it, so I'll tell you in the upcoming classes. So thanks for watching this particular video. We'll see you in the next video. Thank you guys. Bye.